Alright, I was not planning on being out today, so this is not a catch-up day. It is day 4, and I can't really answer your questions from days 1 through 3, but you've all just had a work day within the last 2 class periods, so. Alright, so this is the exact page of the assignment. It's basically just a prep day for day 5, so I guess it's a good day to miss. I'd rather be there. Do at least one problem from every row on the front page, and then do all of 39 through 42. So this is just reducing radicals. You should have done this at least, I don't know, 2 or 3 times before. All this is basically breaking down some number into the product of 2 numbers. So like taking 2 factors, and one of them should be a perfect square. So I'll do, let's say number 9. That's an interesting one. What we have to do is anything that's inside of the square root, you need to figure out what perfect square is a factor of it. So we know that perfect squares are 1, 4, 9, 16, 25, 36, 49. It's just, all of the first few numbers of the counting numbers squared. So like the 7, we're just going to chill. It's going to sit up front because it's not under a square root. We don't care about it yet. The 32 is under a square root. We want to think of what perfect square numbers, any of these and the ones after it, multiply by something to make 32. So we know that 4 works because it's 4 times 8. We can use that, and I'll show an example why we shouldn't use that. But we should use a perfect square, and it will work either way. This would be like square root of 4 times 8, because 4 times 8 is 32. So underneath the square root bar, we'd have that, and we can technically split it up into 2 square roots. That's a property of square roots. And then we know what square root of 4 is, so it's 2. So as of right now, we have 7 times 2 times square root of 8. These are equivalent statements between what we started with and now. Outside and out front, that's 14. But we also have a problem now, is that 8 also has a perfect square as a factor. Like one of these numbers up here can be multiplied by another number to make 8. So 4 and 2 work. This would be square root of 4 and square root of 2, and the square root of 4 is 2. So now we have 14 times 2 times square root of 2, which is 28 square roots of 2. And that's the correct answer. But I'm going to quickly show a better way to do it. So a better way to do it would be to take the largest perfect square that is a factor of 32. Namely, 16 can be multiplied by something to make 32. So that's larger than 4, and it's going to make our lives easier. This 7 is still just going to chill, but the square root of 32 can be broken up into the square root of 16 and the square root of 2. Again, all of this, the whole point of all this rests on being able to recognize which of these numbers can be multiplied by something to make the number underneath the square root. And 16 works, and it's the largest one that there is that goes into 32. So 16 turns into a 4 because we can take the square root of 16. But then square root of 2, you can't take the square root of 2. It's going to be some gross number. So you just leave it, square root of 2. And then 7 times 4 is 28, and we have square root of 2. So that's your answer, just like we just had. It's just that it's faster if you take out the largest perfect square. Very briefly, to follow that up, this guy does have, like number 2, it does have perfect squares in it, and I'd split it up into these 2, but since it's negative, that negative, I'm going to first say there's now an I out front, and it's actually square root of positive 72 that I'm dealing with. At the 72. So anytime you have a negative, just take the I out and put it up front. There's nothing else you need to do with it. there are two numbers that work here, and it's kind of like this one, in which you should look for the largest perfect square. Alright, next page. Alright, so this is something called rationalizing the denominator. And honestly, I'm not a big fan of this because I can't find a reason why we still do this, but just in case you ever do this in a college algebra class, you should know how to do it. You're not supposed to have a square root on the bottom of a fraction. There are some reasons for it, but it kind of doesn't matter right now. What you do is you multiply it, that whole fraction, you multiply it by whatever is in the square root on the bottom. So exactly what the square root is, only the square root that's on the bottom. This would be square root 3. And since we can't just cheat and change this fraction by multiplying it by something, we should multiply it by 1 so that it doesn't change. But we know that the same thing, when you have the same thing on top and bottom of a fraction, that is like multiplying by 1, because it's the same thing. On top and bottom means it's 1. So we can multiply the top and bottom by square root of 3, not change it. On the top we'd have 48 times square root of 3. On the bottom you'd now have square root of 3 times square root of 3. But that's square root of 9. And square root of 9 we know is 3. So this is rationalizing the denominator, except right now we also have the problem in that 48 and 3 can be reduced. The radical cannot be reduced with numbers outside of a radical. The square root is a radical. So 48 and 3 can be reduced. Basically, take a 3 out of both. You would divide the top and bottom by 3. That's messy. And you'd get 16 square roots of 3 on top, and then 1 on bottom, so I'm not going to write it. It's just 16 square roots of 3. All of these are going to be the same. You either reduce it at the end, or you either can reduce it at the end or not, but it's all going to be just multiplying whatever the square root is on the bottom. So this one would be square root of 5 over square root of 5. And then you would deal with all that. And lastly, but probably most importantly for us, because historically this is more difficult, to deal with something like this, and this is often an answer, a type of answer, the way that it looks, that we get when we do the quadratic formula for a quadratic. Yes, that's coming. So let's just do everything we normally did before. This is a radical. We should try and reduce that if we can. The two factors, the best factors that go into 72 that we should break it down into are 36 and 2. 36 is the largest perfect square that goes into 72. 9 does also, but there's more work involved if you choose that. So I'm going to choose 36 as the largest one. That means we have 6 square root of 2. So essentially this square root of 72 part is really just 6 square root of 2. So we would have 12 plus or minus 6 root 2 over 6. So I want to recall for a second, just kind of pause. Here's an aside. If you have, like if we used to have, like, let's say 1/7 plus 3x sevenths. Okay, those are both fractions. They're both fractions. They have the same denominator, so we ought to be able to add the tops. 1 plus 3x. Can't really add those because they're not like terms, but we can put them as a fraction with just one denominator. It's the same thing with this guy. Right now, it's just a plus or a minus in between, so it's the same operation technically. And if we say that they have the same denominator, we could reduce these. We could reduce these guys and that guy. That would be like saying, maybe we had, 7/14 plus 2x 14ths. We could reduce both of these. Sorry, it's a separate problem. We could reduce both of these as 1/2, and then this one would turn into x over 7. We could reduce them separately if we wanted to. These guys, this over here, our original problem. The 12 and the 6 and the 6 and the 6 have the same factors. we could split it up and say that's 12 sixths plus or minus 6 root 2 over 6, and then reduce the whole numbers as we can. So this would be 2 plus or minus, and then 6 and 6 is just going to cancel. You get the square root of 2. You could think of it that way. And so we can split them up, or we can keep them as the same fraction, but just we need to know that the denominator will cancel with both numerators that are connected by a plus minus sign. Not just one or the other, but it has to cancel with both. It has to be reduced with both. That's kind of the trick. So I'll give one more. How about number 40? We know that 24 has a lot of factors, 8 and 3, 6 and 4, 12 and 2, but we're only looking for perfect squares. So this turns into square root of 4 times square root of 6. We chose that because 4 is a perfect square. It's 2 square root of 6. And then we have 4 plus or minus 2 root 6 over 20. Now, 20 has a common factor with 4, and it has a common factor with 2. I'm kind of just thinking, though, like if I want to leave this thing as just one little nice package, like one little fraction, I'm only going to reduce with the smallest number. I'm going to reduce with the 2, with the 20, because 4 has a 2 in it as well. So I could divide it, both the 2, the 4, and the 20. I could reduce all of that by the same number. I could reduce it all by 2. That would give me a 2 plus or minus 1 out in front, so I don't need to write it. And then on the bottom, 20 divided by 2 is 10. We could write it like this as well. Everything got reduced. So this is reducing, like, basically what a type of answer that you would get from the quadratic formula. It's just kind of like fancy reducing that we haven't had to think about before. All right, please come tomorrow with any questions you have on this, because otherwise I won't know how to help you. Good luck.